So, are there particles that travel backwards in time? The short answer is weird. It's a yes, but not in the way you think. It's not about sending messages to the past or preventing your parents from meeting. It's something more subtle, more mathematical, and in some ways, more profound. It's a story about how we look at the universe and the strange rules that govern the smallest things in it. To get there, we have to start with time itself. For most of human history, time was simple. It was a river. It flowed in one direction, from past to future, at the same speed for everyone. A minute for you was a minute for me no matter where we were or what we were doing. Isaac Newton built his whole system of physics on this idea of absolute universal time. And it worked. It worked well enough to describe planets moving around the sun and apples falling from trees. Then Albert Einstein came along and wrecked the whole thing. Einstein showed us that time isn't a universal clock, ticking away for everyone at the same rate. Time is relative. It's tangled up with space in a single four-dimensional fabric he called space-time. And this fabric can be warped and stretched. One of the weird consequences of his theory of special relativity is that the faster you move through space, the slower you move through time relative to someone who is standing still. This isn't just a theory, it's been proven. Clocks on GPS satellites, which are moving very fast high above the Earth, actually tick slightly slower than clocks on the ground. Engineers have to account for this tiny difference, or else your GPS would send you into a ditch. So time is flexible. That's the first big idea we need to accept. Einstein also established a cosmic speed limit. Nothing with mass can travel at the speed of light, and nothing can travel faster. The speed of light is the ultimate speed limit of the universe. The speed limit is deeply connected to cause and effect, what physicists call causality. An effect can never happen before its cause. You throw a rock, and then the window breaks. The window never breaks before you throw the rock. The speed of light is the maximum speed at which any cause can travel to create an effect. It's the boundary of the knowable universe. So, in Einstein's world, traveling back in time seems impossible. To go back in time, you'd have to somehow break the chain of cause and effect. You'd have to travel faster than light, which his theory forbids. For a while, that seemed to be the end of the story. Time travel was for science fiction. But then physics got even weirder. We started looking at the world of the very, very small. The world of quantum mechanics. Quantum mechanics is the set of rules that governs particles like electrons, photons, and quarks. And those rules are bizarre. In the quantum world, particles don't have a definite location until you measure them. They exist as a cloud of probabilities. A particle can be in multiple places at once. It's not a tiny little billiard ball, it's something much fuzzier and stranger. This quantum weirdness opened up new ways of thinking, new equations to describe reality. In the 1920s, a physicist named Paul Dirac was trying to combine Einstein's theory of relativity with the new rules of quantum mechanics. He wanted to write an equation that described how a fast-moving electron would behave. And he did it. He came up with a beautiful, elegant equation that perfectly described the electron. But there was a problem, a huge problem. Like many equations in physics, Dirac's equation had two possible solutions. One solution described the electron we all know and love, a particle with a negative charge and a positive energy. That made sense. But the other solution described a particle that was just like an electron but had negative energy. The one in the world is negative energy. It was a complete mystery. It seemed like nonsense. If negative energy particles existed, the universe should be incredibly unstable. An electron could just keep falling to lower and lower negative energy states, releasing an infinite amount of energy in the process. Everything should collapse. But it doesn't. So what was going on? For a few years, physicists were stumped. They thought maybe Dirac's equation was just wrong, or that you were supposed to just ignore the negative energy solution. But the equation worked so well in every other way. Then came one of the most brilliant and creative physicists of the 20th century, Richard Feynman. He was known for thinking about problems in unconventional ways, for visualizing things instead of just manipulating symbols. He looked at Dirac's strange negative energy solution and had a breathtakingly simple and strange idea. Feynman proposed that a negative energy electron moving forward in time is mathematically identical to a positive energy particle, with the opposite charge of an electron moving backward in time. Let that sink in for a minute. He wasn't just pulling this out of thin air. The math worked perfectly. All the properties of this hypothetical backward in time particle matched a particle that had already been discovered, the positron. The positron is the electron's antiparticle. It has the same mass as an electron, but it has a positive charge. When an electron and a positron meet, they annihilate each other in a flash of energy. So Feynman's idea was this: a positron is just an electron traveling backward in time. This is the core of the answer to our question. According to this powerful and successful interpretation of quantum mechanics, yes, there are particles that travel backward in time. We call them antiparticles. Every particle has an antiparticle. A proton has an antiproton. A neutron has an antineutron. And when we see an antiparticle, like a positron, what we might be looking at is its corresponding particle traveling into the past. Now, this is where we have to be very, very careful. This does not mean a positron has a little time machine. It doesn't experience the past or have any memory of the future. It doesn't violate causality in the way we usually think about it. To understand this, Feynman developed a tool called Feynman diagrams. These are simple little drawings that physicists use to map out how particles interact. They are like a comic strip for the quantum world. In these diagrams, time usually flows from bottom to top or from left to right. A line with an arrow pointing forward in time represents a regular particle like an electron. But an antiparticle, like a positron, is drawn as a line with an arrow pointing backward in time. Let's imagine a common event. A high-energy photon of light can suddenly turn into an electron and a positron. This is called pair production. In a Feynman diagram, you draw a wavy line for the photon coming in. Then, at a certain point in time, that line splits into two. One line is for the electron, with its arrow pointing forward in time. The other line is for the positron, and its arrow points backward in time, back towards the point where it was created. Later, that positron might meet another electron. They annihilate, producing another photon. In the diagram, the electron line moving forward in time and the positron line moving backward in time would meet, and a new wavy photon line would emerge, moving forward in time. From our perspective, living our lives forward in time, we see a photon create an electron and a positron. The positron zips along for a bit, then hits another electron, and they both disappear, creating a new photon. It's a perfectly normal sequence of events, because 1, the first photon leads to effect 1 pair production. Cause 2, the particles meaning leads to effect 2 annihilation, no paradoxes. You can't use this to send a winning lottery ticket back to yourself, but from the particle's point of view, if you could follow that single line on the diagram, the story is different. An electron moves forward in time, gets hit by a photon which kicks it with so much energy that it reverses its direction in time. It travels back in time for a little while as a positron, until it gets hit by another photon that sends it forward in time again as an electron. It's 2 ways of describing the exact same event. The math is identical, so which one is right? Is the positron a separate particle moving forward in time, or is it an electron temporarily moving backward in time? Physics doesn't really give a final answer. It just says that the mathematical model of an electron moving backward in time works. It's a beautifully efficient way to do calculations. It simplifies everything. The idea of antiparticles just pops out of the math naturally, instead of being something you have to add on. For a physicist, when a theory is that elegant and powerful, you tend to think it's telling you something true about reality. This idea led to an even wilder thought from Feynman and his mentor John Wheeler. They had a late-night phone call where Wheeler proposed something crazy. He said, "Feynman, I know why all electrons have the same charge and the same mass." Feynman asked why. Wheeler said, "Because they are all the same electron. This is the one-electron universe hypothesis." The idea is that there is only one electron in the entire universe. This single electron zigs and zags back and forth through time. It moves forward in time, then gets scattered by a photon and starts moving backward in time. Then it gets scattered again and moves forward. The path it traces through spacetime is an incredibly tangled, knotted line. Our universe, as we experience it at any given moment, is just a single slice through this 4-dimensional mess of spacetime. When we look at this slice, we see the single tangled line piercing through it at billions and billions of places. Every place where the line is moving forward in time, we see an electron. Every place where the line is moving backward in time, we see a positron. This would beautifully explain why every single electron is a perfect, identical copy of every other electron. It's because they are, in fact, all the same object, just seen at different points in its incredibly long and complicated journey through history. It also explains why we see a rough balance between matter and antimatter in particle accelerator experiments. Every time the electron turns around in time, it creates one electron and one positron in our slice of time. Now, this is a highly speculative idea. Most physicists think it's a beautiful piece of poetry, but probably not literally true. For one thing, we see way more electrons in the universe than positrons. There's a lot more matter than antimatter, and the one electron universe theory doesn't easily explain this massive imbalance. But it shows how seriously physicists took this idea of particles traveling backward in time. It wasn't just a quirky mathematical trick, it was a concept that could potentially explain some of the deepest mysteries of the cosmos. So, the most accepted answer is that antiparticles are the physical manifestation of particles traveling backward in time, at least mathematically. But are there other candidates for time-traveling particles? There is another purely hypothetical type of particle called a tachyon. The name comes from a Greek word meaning swift. Tachyons pop up in some areas of theoretical physics, like string theory. The defining feature of a tachyon is that it always travels faster than light. Remember how Einstein said nothing can be accelerated to the speed of light? Well, the theory doesn't forbid particles that were always traveling faster than light from the very beginning. For a tachyon, the speed of light would be a minimum speed limit. It would take an infinite amount of energy to slow a tachyon down to the speed of light. If tachyons did exist, they would have some truly bizarre properties. One of them is that, from certain points of view, they would appear to travel backward in time. This goes back to Einstein's relativity, because time and space are relative to your motion. Two different observers can disagree on the order of events if those events are separated by a distance that can only be crossed by faster than light travel. Imagine you have a tachyon gun. You fire a tachyon at a target a light year away. From your perspective, you fire the gun, and a little over a year later in your time, the target gets hit. But for someone on a spaceship flying by at a very high speed, they could see the target getting hit before you fired the gun. For them, the effect would precede the cause. They would see a tachyon emerge from the target and travel backward in time to your gun. This would create all sorts of paradoxes. You could set up a device that detects the incoming tachyon and automatically shuts down the gun, so it never fires in the first place. So the tachyon is detected, but it was never fired. This is a classic grandfather paradox. Because of these causality problems, most physicists are very skeptical that tachyons exist. Also, we've never ever detected one. Every particle we've ever found travels slower than the speed of light. Tachyons remain ghosts in the theory, a fascinating what-if scenario that highlights the deep connection between faster-than-light travel and time travel. So where does this leave us? The idea of particles traveling backward in time isn't science fiction. It's a cornerstone of modern particle physics, but it's time travel on a microscopic quantum level. It's a feature of the mathematical description of our world that works incredibly well. The Feynman interpretation of an antiparticle as a particle moving back in time is essential for the standard model of particle physics, which is our best description of the fundamental forces and particles of the universe. But it's crucial to understand what this means and what it doesn't mean. It doesn't mean you can build a time machine out of positrons. The time travel is part of a self-consistent causal loop. Let's go back to the pair production example. From our forward time perspective, a photon creates an electron and a positron. The cause is the photon. The effect is the two particles. That causal link is never broken. The backward in time interpretation is a different way of looking at the same causal chain. It says an electron was moving forward, got kicked back in time, and then got kicked forward again. But the kicks are the causes. You can't have the electron show up in the past without the photon arriving from the future to kick it there. And you can't change the past because the past version of the particle is inextricably linked to the future event that sent it there. The whole path forward and backward through time is a single event. Think of it like a movie. You can watch the movie from start to finish, or you can rewind a short segment and then play it forward again. The story of the movie doesn't change. All the events are still there, fixed in place. The Feynman interpretation is like acknowledging that the film can be run backward, but the story it tells remains the same. The universe on the smallest scale seems to care less about our human intuition of a one-way flow of time. The fundamental laws of physics, for the most part, are time-symmetric. They work just as well forward as they do backward. If you watch a video of two billiard balls colliding, you can't tell if the video is being played forward or in reverse. The physics is the same. It's only when you have many particles in complex systems that an arrow of time emerges, driven by things like entropy, the tendency for systems to become more disordered. A single electron zipping along doesn't have a strong sense of this arrow of time. So the idea that it could be flipped around to travel backward for a moment isn't as crazy as it sounds. It's just following the fundamental time-symmetric rules of its existence. So, to wrap it all up. Yes, there is a very real, very powerful, and widely accepted sense in which particles travel backward in time. We call them antiparticles. When we see a positron, we are likely seeing an electron on a journey into its own past. And this isn't a speculative fringe idea. It's a key part of the theoretical framework that physicists use every day to make sense of the quantum world. It makes calculations easier and provides a deeper, more unified picture of reality. But this isn't the kind of time travel you see in movies. It doesn't involve paradoxes or changing history. The time travel is a localized event that is perfectly consistent with the laws of cause and effect when viewed from our macroscopic perspective. It's a feature of the strange, probabilistic world of quantum mechanics, a world where our everyday intuitions about space, time, and identity begin to break down. The universe, at its most fundamental level, is not a collection of little marbles bouncing off each other. It's a dynamic, interconnected dance of energy fields and probabilities, governed by elegant mathematical rules. And one of those rules seems to be that for every step forward in time, a step backward is also possible, at least for a little while. It's a humbling reminder that reality is far more complex and beautiful than our simple, forward-moving experience would have us believe. The river of time, it turns out, might have little eddies and whirlpools that momentarily flow against the current.